Thanks, Kitay, for the introduction and also invitation. It was my honor to visit back SNU. This is my probably, I don't know, third or fourth time over the last 20 years. Probably it's a good occasion to tell you a sort of a big overview story about this overall nanowire research field, where it comes from. Okay, I will tell you the story from day one. Okay, so 30 years. Okay, so today I'm going to tell you a story on one-dimensional nanostructure. By itself, it's also a very, very big research field. It started literally about 30 years ago. Okay, quantum dots is much earlier. Quantum dots, we can say it started maybe 40 years ago. Okay. So when we talk about the one-dimensional semiconductor structure, I always start with this particular slide. Okay? And many of these sort of methodology we talk about in terms of how to make one-dimensional structure, it goes back to this very old paper. Back in '64 in APL, this is Wagner at Bell Lab. Okay? And this is back then at the 60s, Wagner actually studied one very special crystal growth methodology called vapor, liquid, solid crystal growth method. And it turns out that flux line pinning leads into the birth of the nanowire research field. Okay, let me explain why. Okay, so back then, many of the, I think, in the chemistry department, MSc and also condensed matter physics community are working on one very important problem. Essentially, we have already have these collection of high TC superconductor, basic copper oxide-based high TC superconductor. They have reasonably high transition temperature, and they also, and people still started thinking about moving into sort of industrial application, but in order to move them into industrial application, you need make these high TC superconductor to carry large current without basically losing energy. Okay, and that's what we call as critical current density. You need that critical current density as high as possible for practical application. I mean, the first idea is carbon nanotube, right? Okay, 91, Yajima published a nanotube. So my first project is embedding carbon nanotube in high TC superconductor. And then that project certainly doesn't go anywhere, because by now we know in order to make these high TC superconductor, we need a high temperature, need oxygen, very oxidative environment. And in that, let's say 1,000 degree and oxygen, the carbon nanotube burn out. Okay. So they will basically, in the synthesis, they will basically all disappeared. And that leads into sort of the first idea failed, then the second idea started to be formulated. In this case, it's germanium nanowire with gold as the catalyst. Okay? Of course, the phase diagram of this binary eutectic system, right? So you have, let's say at gold nanoparticle at 800 degree, pure gold, of course, is solid. Okay. Now, at 800, you start to supply germanium vapor. Germanium start to alloy with gold. Okay. And in the phase diagram, we know it will go into this biphase region. Okay. That's solid gold with some sort of germanium gold liquid, right? If you add more germanium along this isotherm line, then you will reach into the single phase, that's liquid. This is a sort of foundation of the nanowire photoelectrochemistry. You can see VLS method, you can selective deposit and you can electrochemically link them. Okay, this serves as our powerful sort of photoelectrochemical platform, really looking into how much photocurrent we can extract on a single nanowire level. Of course, semiconductor, you cannot get away without heterojunction. Okay, semiconductor, I guess, is the richness of the heterojunction is much sort of broad compared to carbon-based material. Here, you can have all sorts of heterojunction that borrows from the sort of traditional semiconductor industry, the core shell structure, the superlattice. Back then, I think both Charles Lieber's group and my group has spent quite a bit of efforts looking at using silicon nanowire as active channel as the transistor. Okay? And as you can see, the advantage of the approach that my lab has been pushing is basically it's a epitaxial growth of nano. It's a vertical oriented. Okay? And this basically gives us opportunity to do this new architecture. This is at the time we call it surrounding gate, okay? Because you can see we can make these nanowires as active channel. We can make a vertical transistor, but more importantly, now the dielectric surrounding it is surrounding gate. Okay, let me start with the photonic side. So when we start with this, as I said, our focus sort of at that time, we just use CVD, we use VLS, vapor liquid solid, and additionally we added one very important feature is epitaxial growth, and instead of random growth. Okay? Epitaxial growth means all these nanowire is oriented, epitaxial grow on certain substrate. Okay? And that gives us a very unique opportunity that we can grow arrays of them. Okay, by the way, this is non-epitaxial. You can see it's randomly. It's on silicon surface. This is on sapphire substrate. Okay, so it's a epitaxial growth. Being epitaxial, you can see it's all oriented. Okay, it's sort of incremental. Okay, you can just use the same concept to make different wavelengths in terms of laser, nanoscopic lasers. Okay, and here is basically earlier on I said it's core shell nanostructure. It's gallium nitride, only several nanometer, 10 nanometer thick, because it's a huge, highly confined, quantum wire with a sort of a dielectric of aluminum gallium nitride, okay? And that serves as a laser as well. This is quantum wire based, strongly confined system. You can play lots of tricks, again, borrow from the sort of traditional semiconductor laser industry. Two laser cavity, you can couple them together. Okay, and we're called as cleaved couple cavity. They are no longer sort of good thermal conductor. And certainly the superlattice helps as well. Silicon germanium superlattice, this junction further sort of slow down the phonon transport, further decrease thermal conductivity. And that leads into sort of my second startup on here. We can now produce these silicon nanowire with more surface engineering, and that leads into sort of we can mass produce these silicon nanowire electrochemically, and the ZT actually is 100-fold greater than the bulk silicon. Okay? This is really optimize the power factor and decrease by suppressing the thermal conductivity as much as possible. However, this concept actually was proposed back in the 70s, but experimental demonstration is very, very challenging. Okay, let me explain why. 70s, of course, everything is about bulk, just like I talked about VLS in Bell Lab. Everything is bulk single crystal. Okay, this device you can see it's centimeter long. Okay, it's a single. He's proposing putting two single crystal together. Okay, and if you are putting two single crystals together, then one is very low surface area. Okay, that's one. Second, the light comes from one direction, will never have the capability to reach the other side. Okay, so that beats the purpose, right? Same two-half reaction, same two-photon scheme, right? So this sort of, from physics point of view, it's a beautiful concept. Okay? And what we did back in 2003 when we launched Helios program is basically first time we revised the orthognosics bulk single crystal design. Okay, get rid of this sort of single crystal design. Now introducing this nanowire photochemical diode, and that immediately gives us several major advantages. I will briefly explain in the next few slides. One obviously is the high surface area. Okay, and the second, you can design the aspect ratio of this nanostructure to be a single optical path device. Right, so that solves the couple of bottlenecks in the original proposal. Okay? And these are now silicon photocathode is standard photocathode for us now. Okay? Very dark, very effective in terms of light absorption and trapping, and very effective to generate electron as well. And typically photo voltage is to 400 millivolts, okay, for the silicon structure. Okay. And you can see that now the three-dimensional surface is available for us to put on whatever catalyst we can imagine to do our CO2 reduction chemistry, right? Okay, now here's the real sort of energy problem, okay, in terms of when we design this system. So we apply this nanowire diode, titanium oxide. So we have a problem, okay? If we want to apply the nanowire version of photochemical diode concept to CO2 reduction, we have the photovoltage problem, okay? And if you look into this plot, okay, this plot actually summarizes basically electrochemical reaction and the photoelectrochemical reaction. This gap, that basically indicated the photovoltage will gain from the semiconductor. This side is from N-type, this is from the photocathode. If you run the CO2 reduction, you can see after the additional photovoltage supplied, the JV curve is here. These are two sort of relay. They will be reduced, both will be reduced by the solar generated electron. Then ferredoxin and quinone will be used to activate NADH and NADPH inside the cell. Then within this cell, we have the synthetic pathway that drives this 2 electron reduction to carbonyl, and then 6 electron all the way to methyl group, then couple basically eventually is acetate, C2, with almost 100% selectivity. Okay? And you can see NADH is here, NADPH is here, NADH here, reduce the ferredoxin here, participate in 2 electron here. Okay, so this is very well-defined synthetic pathway using biological system. The whole thing actually only wastes 200 millivolts. And those carbon now is all from CO2. Okay, that's the sort of, we offer this synthetic pathway using a very green sort of process, using solar energy as energy input. Okay. And I forgot to mention, the first generation device only have 0.4% solar to chemical energy conversion efficiency. We spent quite a few years to optimize getting into 2.0 version with adjusting pH, adjusting loading, and right now we're at 3.6%. Okay? And keep in mind, all these current from the version 1, version 2, the anode reaction is all OGR reaction. Okay? And that basically is limiting. Okay? OGR, we know OGR side, the titanium oxide absorption is low, so photocurrent is always low, limiting the silicon photocathode performance. Basically, this is just illustration. We can do HER, we can do CO2 reduction. The most important thing that you start to remove OGR from anode side is now photocathode can be silicon, photoanode can be also silicon. Okay, because these two, the silicon, very easily you can do larger scale processing, okay, 6-inch wafer or 12-inch wafer. It gives you 800 millivolts total photovoltage, okay, enough to drive this with their sort of overpotential, especially with our biological version. Okay. We can, synthetic version, we can drive 2 electron reduction, still not for 6, 8 electron. Okay. From both fundamental side, understanding the size-dependent phenomena, to real sort of real-world application as well. Okay. So with that, I want to thank my group. This is my group's 20 years reunion. I think back then half of our group come back, okay, by 2019. 2029, we will have 30 years celebration. Okay, I want to thank DOE and NASA over the years for support. Thank you for your attention. Happy to answer any questions.